So good evening all. So today class day 13. Which day? Yeah. Okay. So coming back to the syllabus. So we are discussing on the CTBT sizing calculations, and right now we are on the CT sizing calculations. This topic we are discussing. So regarding the CT sizing, we have discussed that when we do the CT sizing, so we have to do this CT sizing for each core because we have the multi-core we use or multi-winding we use in the CT. So when we talk about the CT sizing calculations, so we have to do the CT sizing for each core or for each winding. So uh, we have seen in previous classes that mainly we have the two type of the core. One is the metering core and another one is the protection core, and protection core again divide in two parts. So one is the normal protection core, that is the P class core, and another one is the PX class core. So far we have discussed about the metering core we have discussed, and we have discussed about the P class core also. So P class and metering class done, and right now we are discussing on the PX class core, uh, PX class binding, their sizing calculations. So when we talk about the PX binding or PX core sizing calculations, so we need to specify mainly uh, this CTR, the current transformation ratio. We need to specify the knee point voltage, which is called as the VK. We need to specify the magnetization current, or we can specify the RCT, CT secondary resistance, winding resistance. So CTR already we have done. CTR already CTR means the same as we discussed for the protection core and winding and the metering winding. So that would be same for the peak score also. And now we are discussing for the knee point voltage calculations. So for the knee point voltage calculations, we have done already one session, that what is the knee point, and and like what is the basics of the knee point calculations. This all we have discussed. We have seen that knee point voltage requirement or knee point voltage calculations formula as per the IEC also. We have seen, we have also seen that if in case we need to use the P class CT, P class CT core for any unit protection, for any zone protection. In that case, if we need to specify the P class CT core knee point voltage, so how we can calculate the knee point voltage for any P class CT also. So as per the IC, we have seen the knee point voltage for the P class also, but for the unit protection, for the equipment protection, mainly if we talk, so we use the PX core. So for that, now the knee point voltage calculus we are doing. So what we discussed, one more important point, that we are not doing the knee point voltage calculations for the CT. Basically we are calculating this, what is required knee point voltage as per the relay, and the CT knee point voltage should be more than the required knee point voltage by the relay. So we are coming with the relay, and we are doing the calculations for the relays, and accordingly that CT knee point voltage we are deciding. This is this all things we have discussed in a study class day 12. Just quickly, uh, like
Yes, sir. We have discussed that, and we have also you have also told us about the RED 670 ABB relay.
yeah,
Yes,
yes, yeah. So
that is the zone of protection zone you have discussed,
yeah. So
out of substation and inside substation.
yeah. So let's quickly refresh. So the CT knee point voltage, this is all we have seen. Then here we have seen this saturation curve for the CT. So This 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 voltage we are telling as the new point voltage. Uh, Thereafter, the CT core is entering into the saturations because the CT core we designed for the CRGO material, right? And no any core magnetic core is designed for the infinite saturations. So the core will have some saturations. But my requirement is that the CT core should not saturate at event of the fault uh, before the relay operations. Or we can say that the required knee point voltage in the CT should be more than the required voltage by the relay. So the knee point voltage should be greater than the maximum required EMF by relay. So what we are doing that we are calculating the maximum required EMF by relays, different relays. So for that we will go to the relay applications manual, and from that relay applications manual we will take that what is CT requirement given in that manual, and based on that CT requirement given in the manual we are calculating that what should be the CT knee point voltage. So yeah, that this all we have seen in a study class. Just quickly refresh. So this is the CT knee point voltage calculations. uh, I took this extract from the ABB make relay application manual, the same R8670 model for the relay. So you can see here rated equivalent secondary EMF requirement. This given by the relay applications manual, page 20. So line differential protection. If for this purpose we are using, if we are using this PX code CT. So for that purpose, for the line differential protection purpose, the current transformer must have a rated equivalent secondary EMF EAL, which we are EAL, that is larger than the maximum of the required secondary EMF EAL EAL required below. So they have given the equations 1, equations 2. So both equations we have to solve. Both for both the equations we have to calculate the knee point voltage, and the maximum of out of two we have to decide for the CT knee point voltage or the secondary EMF, right? So this we have seen. So this is by given this formula given by the relay. Another, if we wanted to calculate with help of the IEC standard, so we can follow this formula. But as I told yesterday that uh, the best method, or I can say the correct method, is follow the formula given in the relay application manual, because each relay each relay have different knee point voltage or different voltage requirement. And even though in a single company, suppose you are using the ABB make relay. So if you change the ABB make relay model, you are using RED670. If you go to the REL670, if you go to REB500 relay for the bus bar protection purpose that we use. So in a single manufacturer, different relay model have different CT knee point voltage requirement. So the correct method is take the what relay you are using, what kind of the relay you are using. Based on that, you uh, take that particular relay application manual and what kind of relay we will use. So that also briefly we have discussed that where which kind of relay we have to use. So what relay we are using or what model we are using. So from that relay applications manual, open that applications manual or download the applications manual from the Google or the manufacturer library, and go to the CT requirement page and check the formula, and based on that you calculate the CT knee point voltage requirement. Even though if you have any uh, in your mind that I will go to the IEC, so this is what given in the ICP as per the as per the IC standard. And if you want to calculate the knee point voltage for any P simple protection class P class CT, so that this would be the formula. So even though this all we have discussed yesterday, and so we are entering into the CT sizing calculations for transmission and protections relay. So for the transmission and protections relay, we discuss about that what kind of the protections relay we use. And briefly, even though this all we will discuss in the protection module, just for the relay selections we are discussing this point. So the transmission line protection, so based on the transmission line protection, based on the transmission line length, and based on the transmission line operating voltage, we need to select the relay for the transmission line. If my transmission line is shortest small length, when I telling small length, short length, it means the length around 5 kilometer, 10 kilometer. uh, the CEA is telling the length less than 30 kilometer, we can say the short transmission line length. So for the short transmission line length, we go with the line differential protection system. So we will select the relay who have the line differential protection function. If our transmission line length is medium and long transmission line length, then we need to select the distance protections relay. So this all we have discussed yesterday. Whatever you have the queries, note down, and after the sessions, just 2 hours you give me 9 to 11, and after 11 we will discuss all your queries. So note down uh, in pen and paper, then we discuss with me in last. Okay, so transmission line length. So now we are entering into transmission line uh, CT sizing calculations for any transmission line. So the relay selections already we discussed yesterday. Relay we selected. These are the like relay models, and in this relay model we can see that which relay model for which applications we use. Right. So for the line protections, if we have differential protection, so we can use RET 670, RET 650. If we need to do the if we have the long transmission line, so we need to select the distance relay. So for that, the relay model would be REL 670 or REL 650. So this all we have discussed yesterday. And now now how we are moving, how, like, what is our approach for the CT knee point voltage calculations. First of all we need to know what is the protection system requirement, what my protection system requirement. So based on that, we are selecting the relay, right? We are selecting the relay who have the protection function inside the relay. And what is my protection system requirement? Based on that, we are selecting the relay. And once the relay selection done, what make relay you are going to use based on the protection system, then you download the relay application manual. There is many manual for the relay, like technical manual also available. So no need to download, or do not download the technical manual. In the technical manual you will not found any CT requirement formula. So for the CT requirement, the manual name is the application manual. So download the applications manual, and then in the applications manual, you there would be many, like 600 or 700 page would be in the application manual. So no need to read all the 6 or 700 page. Only directly go to the CT requirement, page, and then note down the CT requirement formula. I think yesterday we have downloaded manual. I think we have downloaded ABB uh, RED. Six technical manual also available, but no need to uh, select this. Six technical manual, no connections diagram, nothing. Just type application manual. Applications manual. So this is the link for the ABB library. So now this is the RED 670 line differential protections, because we have decided the what kind of the protections is required, right? So go here, go to the your CT, uh, yeah, mini 724. For CT requirement, go to the requirement and click on the current transformer. You will directly reach to the page. Section 2 requirement, current transformer requirement. So here come to the if you are using the differential protection for your transmission line, then these two equations you need to solve. if we are using the distance protection for the short and for the medium and long transmission line, in that case these two equations we have to select for the city knee point voltage calculations. Anyway, we will take both differential and distance, for that we will discuss, right? So yeah, so the seat protection system relay and protection system, how we can decide? So we can for that we can take the reference, we can take the reference of the tender. We can open the tender and we can read the control and protection philosophy required by particular client. From that we can understand the protection system requirement. Yesterday we have referred the PGCIL control and protections technical specifications given by Power Grid to all their contractor, and from that we understood that what kind of the protection system required to Power Grid, and based on that we selected the relay application manual city requirement formula. We need to check there. Now now going back, this anyway, these all things we have
Excuse,
discussed. Yeah.
excuse me, sir.
Yeah.
Uh, I want to share some my experience.
Yes, yes.
So actually, I got the RFP from a Italy project. They were actually installing the solar PV plant there, and actually they were also requiring us to install the electrical infrastructure, but they haven't given that much detail. Actually, there are various categories of the tender like Cat A, Cat B, Cat C.
Hmm.
So CAT is detailed one in which the IEC is written, but in that they haven't specified the IECs in IEEE. So by default we have taken the IEC.
Hmm. Okay.
That thing, CAT C, that what tender was.
Okay.
So do you have have you done that thing? Have you observed that?
Let's discuss in last.
Okay,
And whatever query you have, whatever things you wanted to discuss, we'll
okay,
discuss
okay,
after the session.
okay, sir.
Yeah. And one more thing, if you don't have just to respond your query uh, now.
Chat
So
box.
whatever project you do, if you do not have any given tender technical specifications by any IPP, because this your case is the IPP kind of the case. In that case, what you can do, you can follow that what kind of the protection system in that country, the grid, the power grid used in that particular country. So if you don't have any given protection philosophy, so you can follow the protection philosophy what the grid follow, and based on that you can select the you can refer the protection philosophy, and based on the protection philosophy you can select the relay, and after that you can open that relay applications manual, and in that you can check the city requirement formula. Okay. uh, Sarvan, Ashwin Prasad.
Okay, sir. Okay, sir.
Yeah.
Yes,
In the same case in India also, in if
yes, sir. Yes,
in
yes.
India, so when we do any IPP project, any so developer don't have such kind of the like a small developer don't have such
Yes,
kind of
yes.
the detailed specifications. So how you will deal with this? So whatever, because ultimately you are going to connect your
In
solar.
short, I want to share my experience that was I was
Yeah, yeah,
undergoing as
yeah.
a trainee.
So
Yes.
just yes, okay, okay. So no worries, no worries.
Okay, sir.
Thank you for sharing your experience. So
Okay, sir.
I'm telling, suppose we are doing any kind of solar project in India also or anywhere. So the developer don't have such protection and control and protections philosophy. In that case, you can follow that country grid protection and control philosophy, and because whatever you are making the solar or wind, you are going to connect with the grid only. So your protection system should be as per the grid protection system. So that's the reason, if you don't have any uh, 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 the developer not given any specifications for the control and protection requirement, in that case you can refer the national grid protection system. And or if you are working for any particular utility, suppose you are not connecting your substation with the national grid. In India we have many state, and each state have their own utility. So you can refer that utility, that particular state utility protection philosophy, and based on that you can select the protections requirement, then protections relay, and then applications manual, and then city requirement. Okay, Ashwin, hope this give you.
Yeah, we have to follow the protection principle
Yeah,
over there. Yes.
yes, yes, yes. Because ultimately you are going to connect with their system, so that system great protection philosophy you can also adopt. Okay, thank you. So let's move to the discussions, and the remaining queries we will discuss once the class in the last of the session. Yeah. So thereafter now, so yeah, relay selections we have to do. So relay selections, in that we went to the city requirement, we need to check. So relay selections done, and then from the relay application manuals we need to take the city requirement formula. So this we have written here, and this formula ultimately we need to solve. So if I open my Excel calculation sheet for the CT's Nepean voltage calculations, if you see in this calculation sheet, ultimately today we will discuss only this sheet, but before coming to this sheet we are discussing the background of this sheet. So make of the relay we uh, uh, like put here, then model RAD 670. So this two cell is clear to everyone. Rated current, the relay rated current means relay connect on the CT secondary side. So the secondary current is 1 ampere, so relay current would be 1 ampere. Relay burden we can take from the relay technical manuals, right? So from that you can, or the relay burden in application manual also given. So from that you can take the relay burden, right? The relay burden. And if you have the relay burden, so from that relay burden, because the burden is VA, you know the A, so you can calculate the R resistance of that relay also, that how much resistance it will offer, right? So this that can be calculated from the uh, relay. So this four cell is clear. Now when I going to calculate the CT Nepean voltage, so for the line differential purpose, line differential protection, in KPP means Nepean voltage, as per the ABB recommendations, minimum Nepean voltage would be this formula. So this formula I took from the same here. I took from here. So if you don't download, EL should be greater than EL required IK max. This is so same extract I took and I put here. Right. So this is for the closure fault. Equation 1 for the closure fault. Equation 2 for the throw fault. So that throw fault and closure fault. And now in these equations, the IK max is the maximum primary funda, means the pure substation fault current. So that is 63 kiloampere. Are the bus bar fault current. So that would be the 63 kiloampere. IK max is done. ISN.
Sir, from tender we have taken that
See,
this quantity.
Ashwin, uh,
Yes.
in last we will discuss whatever queries we
Okay, sir.
have.
No, actually I was. Uh,
Yeah, okay, thank you. Yeah, so IK max is the 63 kiloampere. IT max is the throw fault current calculations. So through fault current calculations, now we will discuss how to calculate. And yesterday we wanted to calculate the throw fault current only. So let us come. So 63 kiloampere is my substation fault current, which we are considering as the closing fault current, and now IT max is through fault current, so that we have to calculate based on the protected line resist impedance. So let us discuss about the through fault current calculations, and let us see that what we discussed yesterday also. So this we have seen yesterday. Calculations cases. So first case, internal closing fault we have seen. Second case is the throw fault. So that all we discussed. This is the case of the throw fault that we have seen yesterday. In yesterday also we have done a ETAP simulations, that through that we seen that the throw fault current would, which is the fault on the remote side or fault on the last point of the protected side. So that fault current value would be lower than the your substation fault current value. So if you see here, if my substation fault current 63 kiloampere, but the throw fault current, this, if my transmission line protected length is 20 kilometers, so after 20 kilometer what the fault is happening, so that fault we are referring as throw fault current. So that value would be very less, which is 15.26 kiloampere only. And when your fault, when your line length is increasing, at the same time your throw fault current value will decrease also. So this all yesterday we have done the simulations with help of ETAP also. So now coming to the through fault current calculation. So through fault current calculations would be my source resistance plus my transmission line resistance. So after that we can calculate the through fault current here, right? So before coming to the through fault current or the short circuit current at the remote point, we need to understand about the short circuit current nature. So we have seen the short circuit current nature, that when any fault happens, at the short circuit current have the two component in short circuit. One is the AC component, that is sinusoidal AC component, and plus they have one exponential decaying DC component, right? So this we have seen yesterday, uh, the nature of fault current. So with the nature of fault current, we are trying to calculate the source resistance and the source reactance. So this what we discuss about the DC component, uh, and the DC component decaying rate depend on the exposure ratio. So again, this all things we have discussed yesterday. So this DC component, and here we calculated the time constant required to decay the DC component when any fault is happening. So you can see here that when the fault is happening, so initially as we discussed yesterday, that fault have the AC component and the DC component, and the DC component takes 47.57 millisecond time to decay. Means the initial one cycle, how much time it takes? 20 millisecond for one cycle. So initial for the two cycle or two and a half cycle, your fault current will have the DC component, and after two and a half cycle or after three cycles, in the short circuit current, it will have only the AC component, because this after 47.5 millisecond your DC component is decayed, and this is the time required to decay the DC component. This all, and if you remember these things we had discussed during the ETAP also, right? In the grid in the grid modeling we have discussed this calculations. Okay, and in this calculations, that how much the fault DC component, how much. So please, plus we also discussed that when you select the circuit breaker, you need not only focus on the AC breaking capacity, you need to focus on the DC component breaking capacity also. So this is the ABB 220 kV circuit breaker nameplate. So the DC component breaking capacity is 61 percentage. So when you are calculating this DC component, so you need to take the time. So that time you need to take from the sorry, you this time is required, and this DC breaking capacity is required. So this both you need to select from the circuit breaker rating plate or the circuit breaker GTP for these calculations. And that all yesterday we have discussed. So this is for the 220 kV. This is for any 500 kV, right? So here we discuss the time constant, and based on the time constant we calculated the XYR ratio of the grid, which is coming 14 40 for the 50 years, and 16 for 60 years it is coming 17. And now based on this XYR we can calculate the source resistance and source reactance. So for that, for before coming to the calculations, let us quickly review the power impedance triangle which we studied during the college time. Let me check the recording. Yeah. So here we have the power impedance triangle. So here on the R, X and Z. So anyway, this all we have discussed yesterday. So now we are starting today's sessions, and we are going to calculate the source uh, resistance and reactance at the 63 kiloampere fault current value, right? And after that we will calculate the through fault current. So coming back to the same Excel, ultimately we will come on this Excel, but the each and every point, the each and every cell, I'm explaining first of all with help of this PPT, and thereafter we will discuss in all this in all this Excel together. So now coming to this feeder calculations. So the calculation of XY ratio for the 220 kV. So this all is my rated capacity of circuit breaker. 50 has 63. So this three cell is done. So if anyone have any query regarding the cell, like you can uh, tell me. Right, DC component. This is the formula how to calculate the DC component in the short circuit current ISC. Means as I told that when the fault happens, so fault current have both AC and DC component. So how much would be the DC component? So you can calculate by help of this formula. The DC component would be equals to ISC peak into E power minus T divided by tau. With help of this formula, we can calculate the DC component, right? So now if you see here ISC peak, how we can calculate ISC peak would be ISC under root 2. So that would be the ISC, means the peak value ISC. So we know that how to calculate the peak from RMS value. So ISC peak is to convert the RMS into peak, we need to multiply it by under root of 2. So that we done here, to find out the ISC peak. Now E power minus T divided by tau. So T is my circuit breaker opening time, that how much time required to open the circuit breaker. So maximum total break time, trip initiation to final arc extension, plus a relay operating time. So we can see that what relay we are taking and what is that relay operations time, and plus the circuit breaker opening time, breaking time. So here we can add both the circuit breaker breaking opening time plus the relay operating time. So here I'm if you, for that you need to refer the circuit breaker what circuit breaker you are taking to that GTP or nameplate. From that you will get the circuit breaker opening or breaking time when the fault is happening. So this T would be your circuit breaker opening time. Here I have not added the relay operating time, but we can add here the relay operating time also. So 40 plus 10, we can see the relay manuals and we can see that how much time required to operate the relay. But what happens that since we are using the unit protections relay, we are using the joint protections relay. So when any fault happen, so unit protections relay not wait for the downstream relay. The unit protections relay is for the equipment protections, so it operate immediately without any time delay or without any intentional time delay. So how much the relay operating time that we can take from the relay manuals and we can add in this circuit breaker opening time. Okay, so that would be my T here. Tau is the time constant. So with help of time constant we will calculate the X by R also. So IDC means would be 61 percentage of the ISC, 61 percentage of the, because 61 percentage my breaker can break. So I'm taking the same that how much the DC percentage we have. So 61 percentage of the ISC. Now putting, even though this calculations already we have done. Okay, so just to refresh the earlier calculations during the ETAP grid modeling we have done. So just solve this formula. How to solve this? You need to, here we have E. So you know the ln, you know the difference between log and ln. Log means log is on the 10 base. Ln means this is the natural log. So you need to take the natural log, or ln you need to take, because ln E ln E or base E, that would be 1. That is the reason. So if I take ln here, so it would be 1 only. So exponential will be removed, right? You can see here, you can see in the in the, just give me 1 minute. You can check here, log and ln, log and ln relations, right? So log and ln relations. So what we are using here, we are using the ln, we are using the ln. The difference between log and ln is the log is defined for base 10 and ln is denoted for base e. And you know that for example log of base 2 is the represented log 2 and log of base e, i.e. log e. Log ln is natural log, so ln e would be e only, right? ln e base to the e would be 1. If you take e ln e value, so that value will be 1. ln e value would be 1. Then the natural log ln e would be 1. So if I took here the ln, so ln e base e, that would be 1. So this is 1 and ln will come here. So how we calculate the here the time constant for to decay the DC component? So take the ln on both side. So this tau would be ln, if you see this k16 is really operating this under root ISC. k16 is what? Yeah, 40 millisecond, right? So k16 divided by ln square root 2 ISC peak will be replaced by under root 2 SC. So ISC peak I write here I under root 2 ISC. So under root 2 means square root 2 into ISC divide by ISC divide by again IBC is how much? 61 percentage of ISC. So ISC under root 2 ISC divided by 61 percentage ISC. So ISC will be cancelled out from ISC. So only 61 percentage will be remaining here, right? And this all T would be on top. So 40 divided by this much, and we are taking round up for the 2 digits. So 2 coming here. Okay. So the final value is coming 47.57 millisecond. So this is the time required to decay the DC component from the circuit. And now we know that tau time constant is equals to L by R, and we know that L is what L by R, and we wanted to calculate the source resistance and reactance. So we know the tau, and now the source reactance and resistance we want to calculate X and R. So we know that tau we calculated, and tau is equals to X by R, and X is equals to tau is the time constant, so that we can how we can calculate. So we wanted to calculate source X by R. So X is 2 pi FL divided by R, and tau is L by R. Tau is L by R, time constant. So 2 into pi into F into tau. Tau already calculated. So we can easily calculate the source X by R ratio. So 2 into pi 3.14 into frequency 50 Hz into 47.57 millisecond watt you calculated, right? So this is how we can find out the X by R. 2 into pi into k10 means your frequency 50 Hz, frequency 50 Hz, k 2 pi f into your tau is 47.5 millisecond divided by 1000 to convert into second, right? So this is how we can calculate the X by R 14.94, and which the same value we have already calculated many times, and that same value we have mentioned here. F frequency 16 Hz, so that value is 70. Now coming to the source X by R ratio calculations. Now, so we have seen that to calculate the source X by R ratio, we can follow the two methods or two approach. The first approach we can follow like this, means we can refer this power triangle formula. We know the X by R already, right? The X by R is already calculated, and now we can take the help of from this impedance triangle formula. So refer to the calculations. Let us come to this calculations exercise now. Fault level calculations for line feeder. So source and system data now we are calculating. Fault level of the source 63 kiloampere, fault level 220, voltage, so convert into same unit ampere voltage, and source x by r is 14. Now this all is your power impedance triangle formula. So as per this impedance triangle formula, what we can see, let me just take this snapshot and paste here. Yeah. So theta how much? Theta how much? We know the x by r, so we can find out the theta. So theta would be tan inverse x by r. So theta would be tan inverse x by r. So just tan inverse x by r 14.94. So tan inverse 14.94, that would be a tan 14.94, and we take round up for the two digit. So 2 coming here, right? So 86.18 degree. And you can do the calculations if you by the Google also. Just take tan inverse and put this 14.94. This value will come here. Okay, so we know the theta now. Theta now we know. So now we can calculate the cos theta. We can calculate the sin theta, and now we can find out the this source resistance, reactance, and impedance. Uh, so first let us calculate. So this is my theta. So cos theta would be just cos into 18.68. So cos theta would be 0.066. So theta 86.86 degree. So this is like cos round up rad. Now we convert into radians this one, and K33 this one. So in the radians it is coming 1.505. So anyway you can also take cos 86.86 degree. So this coming is this is 0.067. This is the cos theta value, and sin theta value will be 0.998 when you have 86.18 degree, right? And you know that sin theta, sin 90, how much, what is the value of sin 90? That is around 1, right? So it is coming around 1.998. Cos 90 how much? 0. So which is coming very close to the 0. Okay. So just to your class simple mathematics. Now we have done this. Yeah. So this cos theta and sin theta calculations we have done. Now we need to calculate this impedance Z, and based on that we will go to the reactance R and X. So impedance Z, this formula we need to follow. Z would be, see, the 1.1 is my margin, so you forget about 1.1. Impedance value will be Vs divided by under root 3 into I SC, right? So Vs divided by 3-phase system we have, so root 3 we are taking here. So that just V is Z equals to V divided by root 3 into I, and we are calculating the source impedance, so we need to follow here the fault short circuit current. And if you remember this, we also have done in this solar power plant short circuit calculations, right? So root 3 into I SC. So this is how we can calculate the source impedance value. So the source impedance value will be voltage divided by root 3 into short circuit current. This is how we calculate the source impedance Z. So this value coming 2.017, right? 2.107. And now once my ZS is done, once my Z is done, source impedance done, we know the cos theta value. So Z into cos theta, it will give the source resistance, and Z into sin theta, it will give the source reactance X. So the same we are doing here. So resistance and reactance. So this, if I highlight, so till here, source resistance is done. I'm just like color this, putting the color inside whatever clear to whatever we have discussed. Source reactance X is also done, right? X by R of the source is 14.91, what already we calculated. So X by R of the source, time constant for closing fault TSF, again the X by R of the source Now we know the source resistance, we know the source reactance, so we can calculate now the source X by R, which 14.9 and 14.91, and based on that we can calculate the time constant for closing fault. So 14.47.646 millisecond, which is close near to this what we calculated earlier also. So the same also we can refer. These two calculations we can apply also. So far the source resistance and reactance calculations we have done. Another, this is the approach number one for the source resistance and reactance calculations. The another approach what we can follow is that this one, the same formula that we applied, source impedance would be Z source is equals to the voltage divided by root 3 into ISC. This formula. Now in this formula, we can find out the source impedance. Once my source impedance is calculated, so again 220 kV divided by root 3 into 63 kilo 63 kA, so we can find out the source impedance 2.061, which is coming similar as we done 2.017. We done here 2.017, so similar. So by this formula and this formula, the result would be the same, 2.016. And then now here the formula is changing. So R resistance, R source is equals to Z source divided by under root 1 plus X source divided by R source. Means X by R, you know. So from that R source and X source we can directly calculate. See here. So Z is equals to R square plus X square. So we wanted to calculate the R. So what would be, how we calculate? So Z equals to R square plus X square. If you calculate the R, so that would be Z divided by 1 plus X by R square. The same we have done here. R is equals to Z divided by 1 plus X square plus R square. Similarly, the X also we can calculate. So once we know the R, so X would be Z square minus R square under root. So that would be the R. So this value same as we done. In this we are not converting anything into cos theta and sin theta. Not converting. Without conversion into cos theta sin theta, we can directly calculate with the help of the power impedance formula, impedance triangle formula. Yeah, so far the source resistance and reactance is clear, right? Just uh, like let me know, is that clear? uh, Almost 1 hour done for the class, so am I clear so far? Yeah. I'm trying to keep it very simple, and whatever I'm discussing with in this lecture, for that each and everything I'm trying to explain with help of the uh, uh, this presentation also. Now we need to calculate the through fault current also. For the through fault current, how we can calculate? For through fault current, how we can calculate? Now, as we discuss, so before coming to this calculations, as we discussed that through fault current is what? Through fault current is what? The source impedance, ZS we already calculated. So to calculate the through fault current at the fault at the remote end of the protected line, transmission line, we need to add this, we need to calculate the impedance till this point, till the protected point. So for that, what we are taking, till here we know the resistance and reactance that we calculated based on the source short circuit current and the voltage. Now from the substations to the last point of the transmission line, this transmission line conductor resistance and reactance is required. So for that, uh, what kind of the conductor we are using? Because we have many type of the conductors, like we have the uh, moose, zebra, panther. So what kind of the conductor we are using? What is the diameter of the conductors? What the configuration of the transmission line? So based on these parameters, the transmission line resistance and reactance decided. So for that we need to ask, are the transmission line conductor resistance and reactance from the client or the transmission line contractor, from the transmission line conductor. So now after the source resistance and the source reactance calculations, yeah, the ultimately motto for the source resistance and reactance resistance and the impedance calculations, Bharat, is the through fault current calculations. So for the through fault current calculations, you need the impedance till the last point of your transmission line. So till subsystems, we first of all we calculating the resistance and reactance, and in that resistance and reactance we are adding the transmission line resistance and reactance, and after that we are calculating the impedance at the last protected point. So once you know the impedance, you know the voltage. So based on the impedance, based on the voltage, you can find out the fault current. So this is the purpose why we are calculating the source resistance and the source impedance. Clear, Bharat? Let me tell you. Let me tell you why we discussed the source resistance, reactance, impedance. So if you refer this through fault current calculations, so resistance till the protected point. So the RS is my source resistance plus RL is my transmission and conductor resistance. So we are adding both resistance, then we are calculating the final resistance, and then we are calculating the final reactance also till the point, uh, till your uh, till your transmission line last point. If the fault is happening there, so that fault we are calculating now. So source resistance and reactance we are adding, and then we are calculating the resistance and reactance at the fault point, and then we are finally calculating the impedance at the fault point Z, this much, and then with help of the Z we are calculating the fault current I through three phase fault current, which is coming 34602. So once my through fault current calculated, then the same fault current I will go and I will put here. I will go and I will put here in the second equation. First equation is all the inputs of first equation is clear, but the second equations, let me check from here. 2 IT max ISN this much. So this all we know. Now this IT max we wanted to calculate. So IT max is the through fault current. So for the through fault current, uh, we are like calculating the source resistance and impedance. Yeah, clear all that why we done the source resistance and source reactance calculations. Uh, okay, thank you all. So yeah, now once the source resistance and reactance calculations done, and for that because we are not aware how many what is the how many plant transmission substations coming, where the generator plant is locating. So for that I am taking the reference of fault current. So if the 63 kiloampere fault current, 220 kilovoltage we have. So for that voltage, that fault current, how much impedance will offer? So through that we calculate to the source resistance and uh, resistance and reactance. Okay, Mustaqil, Alam, I think I replied to your query as well. Yeah, so just give me your next one. Huh? So now once my source resistance and reactance is done, so now after the source resistance and reactance, yeah, 63 kiloampere fault current taken from the grid regulations. Yes, right, Bharat. Or whatever your subsystem fault current, you can take that fault current. That this it's my subsystem fault current. We are uh, in India we have for 220 kV 40 or 50 kiloampere, so I will take 40 or 50 kiloampere. We can take 40 or 50 kiloampere also. So whatever my grid fault currents, grid regulations, so that is taken here. Okay. Yeah. Now after the source resistance and reactance, uh, for the through fault current calculations, we are coming to the transmission line. We are coming to the transmission line. Now we are covering this, discussing for this much, Z and this much. So for the transmission line, now after the source resistance and the source reactance calculations, we need the interconnected transmission line resistance and reactance value to calculate the short circuit current value at the remote end of the transmission line. Are the We need to calculate the through fault current. Therefore, the transmission line total length, transmission line resistance, transmission line conductor reactance per kilometer are for the entire length value. We need to ask by client or the transmission line construction contractor, as it depends on the transmission line conductor type, configurations, diameter what they are using there. So we need to ask them before starting the calculation. So what I'm doing, that along with this calculations I'm also making a list. So whenever whenever your project manager asking you to do the CTVT sizing calculation, so what you will ask them, what you will ask to your project manager before starting your calculation. So voltage level, from the system, from the tender, you know, the voltage or system short circuit current, from the tender, you know, the system short circuit current. Transmission line length, now we'll ask, and transmission line positive sequence resistance and reactance you will ask. Why not the negative sequence resistance and reactance? Because for any static system, the line positive positive sequence resistance and reactance is equal to the negative sequence resistance and reactance. So negative sequence you don't need. And why not the zero sequence? So the zero sequence will come when the single phase to ground fault will happen. In that case you require the zero impedance calculations. We will take zero impedance also, in the calculations we will discuss that also. So you can ask zero sequence impedance also, but if you are not getting the zero sequence impedance, so no need to wait, you can start the calculations. Okay, so coming back to the transmission line. So if we receive per kilometer value for the resistance and reactance, then we need to calculate for the total length resistance and total length reactance value. And whenever you are asking uh, whatever value you are getting, you need to cross check that this is the total length value, uh, resistance value and reactance value, or this is the per kilometer value. If your client is telling that this is per kilometer value, then you can multiply it by total length and you can calculate the value for the total length, right? Let me show you one project case for the transmission line. So we are doing a project. So in that case we ask the transmission line this resistance and reactance. So what we got from the client, what we received from the client, so that snapshot we took here. So interconnected transmission line data we have to ask from grid company, from the transmission line contractor. So there are many interconnect, there are many transmission line way we have. So now there is one more important point. If you have, because in one substance you will not have only one transmission line, you will have maybe 5 6 or 8 or 10 transmission line. If you see your the tender that I have given, in that also there are many transmission line. Let me just quickly show you the tender given you but given you there is one important catch here. There is one important catch here. That's why I'm referring this, the tender, the scope of the work written in the tender. So what you can do, there are many, like line by four numbers. So if you are getting the line four numbers, so no need to do the calculation for all the four numbers way. You, for that which way you can select, I'll tell you that for which way you need to do the CTVT sizing calculations. For number of bay, suppose in this we have, so whatever the number of bay we have, all the number of for all the line we got the this length from the client, because we are on the substation side only, so we are not aware with the transmission line length, so that also we need to ask. Then positive sequence impedance positive sequence resistance 0.3552, positive sequence reactance x1 ohm 1.625, zero sequence resistance, zero sequence reactance, and impedance also we have, right? So now what we need to do, we need to add both the resistance and reactance to find out the through fault current, or to find out the impedance at the fault point. So exercise for through fault current, total resistance would till the fault point would be total source resistance plus connected transmission line resistance. Similarly, the reactance, total source reactance plus the transmission line reactance. So total source resistance 0.135 ohm, just we calculated right now. Here we calculated the source resistance in the yellow, R 0.135 ohm, right? 0.135 ohm. Total source reactance 2.012, 2.013 ohm. So that we just calculated. Now the transmission line resistance and reactance we got 0.356 ohm and 1.625 ohm. Here 0.356 and 1.625 from the grid, from the client. So now we add both the resistance and reactance. So total resistance, total source resistance plus transmission line resistance. Similarly, total reactance till the fault point, total source plus total transmission line reactance. Now you know that why we did the calculations for the source resistance and reactance initially. So this we already know, and this we know from the grid company. So now we add both the resistance. So through fault current calculation for three-phase fault, for the three-phase fault. So again the formula that we are going to follow, I is equals to Vs divided by root 3 into Z. So Z we need to find out. We already know that is 220 kV. I we want to calculate. So the R resistance through through three phase RS plus RL, so 0.135, 0.356419. Let me go to the Excel now. So same table one we put here the transmission line data what we got from the client. So transmission line tag number if we have, so that we can put here voltage and which voltage, configurations, conductor what using, circuit how many circuit, one circuit, two circuits, positive sequence resistance, reactance, susceptance B, zero sequence resistance XB. Okay, so we got this value 0.962 because we got this value. If you see here, we have done some formula here. So total length is 3.57. We have the total length right now. We have seen here the length. Yeah, 3.7 kilometer length of we have. So total resistance we have 3.6 3.55 3.56. So we calculated the per kilometer resistance here. So total resistance divided by the total number of length of transmission line 3.7 kilometers. So it gives the total the R per kilometer or the X per kilometer. But if you are not putting, so you can directly put here. If you are not converting per kilometer, so no need to calculate. You can directly put the total resistance and total reactance also. No need to convert per kilometer, right? So here, so we got this Rx positive sequence rest zero sequence. This value we put in this Excel. Number of circuit one, so length 3.75 kilometers. So here this positive sequence resistance, so 0.9622 ohm per kilometer per circuit. So total resistance we calculated now. Positive sequence resistance, reactance, zero sequence resistance and reactance. This just we have calculated. Whatever the given value we have in this value divided by 3.7 kilometer, it will give the per kilometer circuit resistance and reactance. Okay. Yeah, uh, I'll tell you, don't worry. So positive sequence impedance of the line resistance would be 3.5. So I have, because this is my standard format that I follow, that's why I converted all value into per kilometer. So you need to put direct value here, whatever you are getting from client directly here. R this one and X this one. Okay, Bharat, you forget about this because this is my standard sheet what I follow. That's why based on the standard Excel sheet I put converted here. But yes, no, you no need to do this much exercise. Directly we can put the R and X here. If you see here, ultimately I am getting the same value which I got here. Clear, Bharat? This is clear to all of you. Am I clear? Yeah, and what about others? This is the source resistance and reactance. This is so. And now just calculate the impedance, source impedance 1.644. If you don't need to calculate, don't worry. You directly have the impedance 1.66. So directly you can put this 1.664 value. Okay, yeah. So now this is the source resistance, reactance, source impedance. The same under root square root r plus x square source impedance. Now the same exercise I did for the zero sequence impedance also. So if you see zero sequence, the resistance and reactance same as we received input here, that I can put here 0.89 and 5.5722, and the zero sequence impedance is square root of something that we can calculate, right? Yeah, 5.572. Okay, so far this all excel. Few cell we did extra, but this excel so far it is clear. So this much portion of the excel is for this transmission line resistance and reactance. Now zero sequence also we have done. So now coming to the through fault current calculation. So again, resistance till my protected point. So Rs plus RL1. So this we calculated 0.135 my source resistance plus 0.356 was my line conductor resistance. So the total resistance I'm getting, that is 0.491. Similarly, the net reactance I'm getting till fault locations, that is 3.638. So R and X no, so we can find out this impedance Z is square root of Rs plus X square, 3.67 ohm value we are getting here. So once we know the Z, so we can find out the I. So I is equals to V divided by root 3 into Z. So we divide by square root 3 into Z, 3.67 ohm, which is coming I 3 through 3 phase fault 34602 kilo ampere, which done here, which calculated here. Okay, x by r of the three phase fault. So x by r till the point of fault, if we wanted to calculate, so that we can also calculate, because we know the r and we know the x. So that would be this much 3.6338 x by r 4.91, which is coming to 7.41. If we wanted to calculate the time constant, so that also we can calculate the time constant, right? But this is not required in the Rayleigh formula, but if we want, so we can find out also. So now one more thing here we need to here we need to like check that if any fault is happening, so there would be like phase single phase to ground fault that maybe happen. This is the one fault, any conductor broken and like coming on the ground, single phase to ground fault, are the most the most severe fault, that would be the three phase fault. All the three phase sort together, so three phase fault. So similarly we this fault what we calculated, this is the three phase fault. If we want to calculate the single phase fault, so for the single phase fault, whatever the zero sequence resistance and reactance you are getting, so that you have to use, and based on that we need to calculate the the single phase fault value based on the zero sequence resistance and zero sequence reactance value. So if you see here, the zero sequence resistance reactance value is higher than the positive sequence resistance and the reactance. That's why the zero sequence impedance would be higher, and that's why the zero sequence the single phase fault current value, because impedance is higher than fault current value will be lower. Just to show you, just to show you, three phase fault 34.602 here we are getting. Now coming to the single phase fault, so again the source resistance are we are calculating, but now in this case we are using the this zero sequence value. If you see this fault current value, so this is which is coming 28.085 value. So what I wanted to tell, comparing, taking both the case, that when you are doing the calculations, if you go with only three phase fault current, so that is also enough and sufficient, right? So here your three phase fault current value you need to take here. Single phase fault current, if you want, you can avoid also. But if you want to calculate, yes, here we have the formula. So resistance, source resistance plus resistance and reactance we can calculate, then impedance we can calculate, and then uh, fault current we can calculate. But better to go with the three phase fault current. So once my three phase fault current is calculated, so let's go to the calculations. So now in this calculations, so I K max 63, IT max 34602. I hope that now you are clear with the IT max, that how this 34602 current is coming, right? CT have the, yeah, thank you Karthik. CT have the uh, two tappings, multi ratio and multi-core. So they have the two tappings, 2000, 1000. So this is my rated primary current of the CT. Right. So I need to correct this value 3150 whatever written. This is my circuit breaker, not the CT. Okay, CT is this much, 2000, 1000. Rated secondary current of the CT is 1 ampere. Rated current of the ID would be 1 ampere, that same as the relay secondary current. Now RCT value, in if you remember, in the metering core CT calculations, we have discussed about the RCT value, uh, that how to find out the RCT value. So in the metering core, the RCT value we took the ref, uh, uh, we discussed that we will follow what as per the grid regulations, that I hope that I have seen you one table also, that how to take the RCT value. And if you not wanted to, if you don't have any grid regulations, if you wanted to calculate your CT resistance, or that would be better if you follow the grid regulations, the standard 220 kV or 400 kV CT resistance part, uh, like consider in the grid. So same resistance and reactance value we can use here. Or another case, that we can take this RCT from the CT manufacturer, that which CT we are going to use, so that RCT value we can also take the reference. And again we have discussed that if we have executed any previous project, so from that project the RCT value we can also take. Anyway, we have discussed. Yes, the RCT value we will get from the city manufacturers also. Yeah, Richa. Okay. So this RCT, same as we discussed for the metering code. RL is the my lead resistance. So lead resistance already we have done the discussion for the metering code. This lead resistance from the CT till the meters. So that already discussed for the metering code. So that already covered, right? This RL. I hope that you are getting the RL. What I mean by what is the meaning of RL? Just please active on the chat box that you are getting or not getting. If not getting, so I'm ready to repeat all these things, because these things already we discussed for the metering code. That's why I'm referring, telling that you can refer same discussion what we have done for the city metering code. Okay, for that. Okay, Mohammed, thank you. Yeah, yeah, lead resistance, correct. Congrats, the lead resistance. So that what cable, what size of the cable we are using, what is the length of the cable. So based on that, we calculate the lead resistance, right? SR the relay burden, SR is the relay burden. So that you can get from. I hope that you can get from the this applications manual. So if you see here that SR not discussed, so SR you need to take from the your relay application manual. So the burden of ID IET current input channel, VASR would be 0.2 VA per channel for IR 1 ampere. If your relay current is 1 ampere, so for that the SR would be 0.020 VA. So that we are putting in this calculations 0.02 VA. The SR, this SR here. Okay, SR here 0.20. Now coming to the calculation, so the same formula I enter into the Excel. Nothing any extra I have done here. Same formula I put in the Excel and apply the like all the multiplication here. 1.1, please, 1.1 is my margin, means whatever city I am taking that have 10 percentage extra from the real requirement. That's why 1.1 I put here, because 1.1 is not given here. 1.1 is not given here, so 1.1 in this calculation is my margin. So 1 followed by 1.1, because which that is the margin. So IK max, into IK max, let me IK max into ISN divided by IPN. So ISN is 1 divided by primary current, whatever now we have the two tappings. So two tappings, 1000 and 2000 for the city. So we need to calculate the new point voltage for both the tappings. Suppose I am taking the 2000 ampere tap. So at tap 2000 by 1 ampere. So my CT primary current, the CT primary current, IPN would be 2000. So 1 divided by 2000, just it. So one IK max here, IK max is my fault current. So fault 63 kiloampere multiplied by 1 divided by 2000 multiplied by all in the bracket. So 63 into RCT is my 10 ohm. Just let me zoom out this so that you can see that what we enter here. So 63 kilo per IK max into RCT 10 ohm of the city resistance plus RL my lead resistance plus RR my relay resistance. I can if you see here, SR divided by IR square, what it gives? SR divided by IR square, what it gives? It gives the burden, the resistance, right now. Um, um, it gives the resistance only. We know the power. SR is the VA rating, VA power. So V is equals to what? V is equals to what? V is equals to IR. A is equals to I. So VA we can write as the I square into R. So I square into R divided by I square. I square here. So I square cancel from the I square. So only R will remain there, right? So that I am putting here. So VA I can the VA divided by I square R would be only R. So that same value I am putting here, R of the relay. So that would be, if your VA is 0.20, your A is 1, so the burden would be 0.20, all this much. So the R 0.02. Okay. Yeah. So 10 plus 5.758 lead plus your relay resistance multiplied by ISN this much 1 divided by 2000. So this much into 1 divided by 2000. So how much value is coming for the closing fault conditions? EL 547. This much. I just like multiplied all this. So solve this, it will come 547 voltage, right? So if you see this, there is one more point. This is telling that, let me check, current transformer requirement for city according to other standards. Other standard they are telling here. Current transformer to IEC this much. Okay, current transformer according to IEC class PX, IEC 600, class TPS, and old British standard class X. So class X, British standard tell us only class X. So they are telling that in this that city current transformer should be E knee, CT knee should be equal to EK, and that equal to E knee PS British standards, that EAUAL, which shall be greater than 0.8 into maximum EAL required. So that's why due to equation 8, I took this equation and I put here this much 0.8 into EL required. E knee should be higher than 80 percentage of this only. So E knee should be higher than 438 voltage. It that in CT minimum knee point voltage should be higher than 438 voltage. But for the better case, do not take 438, do not take 547. You go with like here already we have done the 1.1 margin. So better to keep 600 voltage or 700 or 800 voltage. That would be better. Anyway, but this is for the this is what exactly required, minimum required by the relay. Second case, if we have now this equations for the Trojan fault only, for the Trojan fault only. Now we need to solve the equation number 2 also, which is for the through fault cases, through fault case. So again 2 into IT max, same things, but in this case what need to change, just you need to change the fault current value, which is IK max, and now this is IT max, and 2 is given in the formula only. So 2 into IT max, so 2 into 34602 into this much as we have done here. So this value is coming 601 voltage. So 481 voltage, this CT Nippon voltage should be higher. So out of these two, which one is the higher? So 481 is higher, so that should be minimum available Nippon voltage. So if we go here, if we go to the CT saturation curve, so this voltage, this voltage should be greater than how much? 481. 481. This is for the closing, for the line differential protection case, right? Now we have, since we have the two tappings, two ratio we are using, so the same we can do the calculation for the another tap, which is 1000 ampere. So same formula only, what going to change, that the current, now we are dividing, initially we are dividing by 2000, and now in this case we will divide by the 1000 only. So add tap 1000 by 1, 1000 by 1. So 1000, now 1000 here. So this is initially 2000, now it is 1000. So what will happen? This much will going to increase. So this much is 747 voltage or 598 voltage, and for the through fault case 657 voltage. So now out of 4 you take, and then you, like for the this two, for the 2000 tapping maximum of 2, and for the 1000 tapping maximum of this 2, we can select, we can select the CT need point voltage. Now this, if we have only the differential protection, so the calculation is done. If suppose for we are using the distance protection feature also, so the CT sizing we have to do considering the distance protection function also. So now if we go to this catalog, here the distance protection case we need to understand. Okay, so coming to the distance protection, so let us take a 2-minute break. Thereafter we start again. Are you guys okay to continue, so that we can discuss the next 1 hour? Next 1 hour. This is the what for the distance protection. So it's going to take the time. And yeah, before coming to the distance protections, I'll first calculations. First, we will discuss about the zone, because protection zone, and after that we will go to the calculations. Okay, so now for the CT dependent voltage requirement for the distance protection relay. So for the distance protection relay, first we will understand about, if you see the formula, we have the formula, we have IK max and IK zone 1. So we will first understand about the zone and how many zone available and which zone we have to take, and after that we will discuss about the city sizing calculations. Okay, so let us connect again after 5 minutes and then discuss the city requirement for the distance rate. Yeah, 5 minutes. Yeah. No, no. See, Mustakal, if your manufacturer change, I already told what you were asking. Already I addressed. If your manufacturer is changed, if your relay model is changed, your formula will change. I will show you. If let me check. Let me show you if I have few other catalog available in my system. At present, I will module 2 CTPT. Let me show you if I have any other uh, few different CT relay catalog. See, if you are using the bus bar differential protection for the bus bar protection, then we use the RAV 500 relay. So for the RAV 500 relay, if you see the formula is changed. Current transfer record for the stability during external fault bus bar protections. So P, N, PE, PB, PE you have to take. N is the rated accuracy limit factor. If you are using the P class code, then if you are using the PX class code, then the same you need to check the formula for the PX class city code. Here it is going for the P class city code. Anyway, the point is that it will change. Let us suppose we have the REC 670 if we are using the BCU. So if you see here, in this case, the city requirement breaker failure protest CT must have rated equivalent limiting secondary EMF. And if you see the formula change now, 5 into IOP IS this much. This much the similar 5 into IOP IOP is the primary operated value ISN divided by IPN, and 5 we have to multiply. Primary operated value, I think that would be the primary current, primary operated value, IOP, primary operated value, A, CT current, IPR, ISN, ISN, RCT, RL, IOP, the primary operate value, that relay primary operate value. In anyway, the formula is going to change. I will check that what is IOP primary operate. The primary current set value of the inverse time function, that how much the value we set to operate the relay. So that is my primary operate value. Relay button, now if you see the relay button is also changed. Okay, so let us see the breaker failure protections. So if we are using the breaker failure protection, so this much non-differential instantaneous different time phase. So you need to check that what for this relay what kind of protection you are using. So that formula you need to pick here. Directional phase and residual overcurrent protection. So this formula will come. So the formula would change. No, no, any other. Yes, yes. One more parameters will come. Yes, the parameter will change. The parameter will come, that is the A and K. The parameters, the another parameter is A and K. A and K. So that's why I will discuss A and K case. So this is the only change we have in the difference and distance protections. Okay, Mustaqul. Okay, so let's reconnect after 5 minutes.